Can you all hear me okay?
Yes.
Okay, let me plug in my microphone again. I will be using a second camera, so let me unplugging my microphone at times. All right. I want to talk about our next lab. And to me, it's an important one because you're going to be learning how to use an oscilloscope. So the Oscilloscope Lab, let me expand the picture. This is your Oscilloscope Lab. I updated it because there was a problem with the file. There was actually something, a substantial amount of it missing. I'm not sure what happened. And so I emailed you the updated version, and then I put a new one on Canvas. And so you're going to be doing basically a skill demonstration, but you're also going to be doing a measurement for me for this lab. The first part, you're going to make a video illustrating to me, showing me that you know how to make measurements with your oscilloscope, okay? And you're going to submit a video and this document. So in this document, you're going to fill out the information about the signal that you analyzed. And then in the second part, which doesn't require the oscilloscope, you're going to be characterizing a signal. You're going to be characterizing the signal generator that you're going to be using along with the oscilloscope. And that signal generator you're going to be using in the last two labs of the semester. So after the scope lab, there's only two labs left. And so there's some issues with the signal generator. We had some issues with it last semester, and so we kind of have to characterize it and understand what it's doing. At least some basics of what it's doing. In fact, there's a couple buttons on the signal generator in which there's a button on there that I have no idea what it does, and I looked it up on the internet, and people who evaluated the signal generator don't know what one of the buttons does, but we're not going to use it anyway, so. So we're going to characterize the signal generator. You're just going to collect some data and enter it in the table at the bottom. Now, this table at the bottom is a little bit different. It's an embedded Microsoft Excel object, which means that if you double click on any cell here, Microsoft Excel will open up. And so as you enter values in Excel, they'll actually show up in the table. So I'm actually going to enter a value in Excel. You can't see me doing it right now. And then I'm going to close Excel. And it shows you the data that I entered. Okay. So you're going to be entering data in the second and third columns of this table, and also in the top, this yellow box. I set up the spreadsheet so that the spreadsheet calculates the important information for you, so you don't have to do all the work. I'm trying to minimize the amount of work you have to do for this lab because I really want it to be more of a skill demonstration lab. But we need to characterize it, and I didn't want to put this in the next lab just because I didn't want to make the next lab too long, so I did it this way. So the spreadsheet, once you enter values, it'll actually calculate automatically what the resistance of the signal generator is. It's actually the fancier term for it. It's called impedance, and we'll talk about impedance when we get to chapter 33. But we need to know its characteristics as a function of frequency so that when we do the lab next week, the new lab next week, we can account for the resistance of the signal generator. Because if you don't, you're going to get huge errors. Okay? So the lab is two parts. So the second part, each part is worth 10 points. Okay, the first part is just showing me how to use a scope, and it should be pretty straightforward. Your video will be around a minute, maybe it could be a little bit longer than a minute, but for sure it's not going to be longer than 2 minutes. Okay, it should be a short video. You just got to show me that you know how to use a scope. That's all. And then this data. So you're going to submit this document along with your video. Questions on that? Okay. And what was missing was this second part of the lab. I mean, half of the second part of the lab was missing in the document. So I spent time last night adding it. And so I'm hoping that the instructions are specific enough for you to be able to do the second part. Okay. So before I go on, let's direct our attention to what I have on the board on the left. So this lab will be doing the 25th. You can probably do this in a day or two. This is a quick lab. There's not a lot in terms of the write-up. I tried to minimize the write-up as much as possible. Okay. The motor lab is doing the 30th. If you haven't started, please start it. And again, if you have questions, please use the discussion board. Because then everybody, I mean, a lot of people are going to have similar questions. Okay. So use the discussion board. I forgot to do one thing on my Zoom. I forgot to pin myself. Okay. There's a module for this lab. Please read all the documents associated with this module. One, you want to read the lab, okay? And I have instructions on how to use the scope in the lab. That was a generic set of instructions because it's for any kind of scope. Then there's also a set of instructions I added that are specific to our oscilloscope and our signal generator. So please read through them. They should be straightforward. The signal generator is pretty easy to use. I will be demonstrating it to you in a few minutes, okay, or really towards the end of class. So make sure you watch all the videos in the module. I put 3 videos last night on the scope and a couple other things, features of the scope that you might want to watch. As I was working on this lab last night, I saw there's a bunch of great videos by a company called Keysight. They make oscilloscopes that are tutorials. They're kind of short, and then the people in them talk kind of fast. But if you use those videos and then look up some other information from other videos, you can learn a lot about the scope. These videos are 2 minutes long. I think so. There's 3. I think if I remember correctly, I think I put 3 2-minute videos. Okay, so it's 6 minutes of watching. Okay, to talk about some of the details of the scope. In fact, their website has a whole bunch of them, a whole bunch of videos. They're 2 minutes long regarding the scope. So you can learn a lot from Keysight. Okay, another company is called Tektronix. They also make a bunch of videos on how to use the scope. And then, of course, I don't know if you've seen the Electroboom videos. Electroboom has like a 15-minute video on the scope. Okay, so you can take a look at those videos. But I didn't put Electroboom's video on there because it's not captioned. So watch all the videos in the module. There's only 3 of them, so it's 6 minutes of viewing. Read the manuals that come with the scope and the generator. So the document I have for the instructions on the oscilloscope don't have every single detail of the scope and generator as the manuals do. So you want to look at the manuals. And look, if you read through the documents, watch the videos and the manual, and read the manuals, it's going to take you a lot less time to do this lab as opposed to not reading anything at all. If you don't read anything at all and try to do the lab, it's going to take you a lot longer. So it's up to you whether you want to spend a long time doing this lab or reading the stuff you're supposed to read and complete the lab quickly. Okay, so that's up to you, I guess. One thing I forgot to mention when I sent you the email regarding the Ohm's Law lab, there is a grading code that I've developed for the labs that you turn in, the written labs that you turn in. That allows me to grade faster. So when I see a sig fig error, I don't have to write the word sig figs out every single time. I just write the letter A. And if I put a 1 next to the A, that means that the answer should have been 1 sig fig. Okay, if I write a B, that means you messed up on the units. Or you don't have any units. So I do have a code. And then anything with the letter G has to do with the mistake you made on the graph. I think G6, if I remember correctly, was no, you don't have a figure caption. Okay. So I grade it that way because it allows me to grade faster. So the grading code is there, and it allows me to grade a lot faster than writing sentences out. It takes too long to write sentences out, especially on a tablet. Okay. Now I want to mention one thing. I want you to make when you collect data. Whatever you do for your lab report, it got to make sense. Okay. So I want to tell you about one set of data that I got for Ohm's Law, where the student measured, and there was more than one student who did something like this. But I want to particularly mention this one. We have delta V here, and I here, and somehow they got a straight line. And for part 2 of the Ohm's Law lab, you were supposed to use a 1,000 ohm resistor. It says in there, use a 1,000 ohm resistor. But this one student used a 47 ohm resistor, and this is not the only student who did not use a 1,000 ohm resistor. Okay, but the reason why I picked this one is because it's the lowest resistor, and it should cause the most obvious problems. So when you put 12 volts across this resistor will be using up 3.1 watts, which is 10 times the rating for this resistor, which was a 1/4 watt. It's more than 10 times, like 12 times. That thing should have been smoking. The graph should have looked like this. But it didn't. So, that's concerning to me. When that bothers me. And if all of a sudden now you have really a resistor that's defying the laws of physics. Okay? So make sure that your data makes sense. Okay? To me, something was fishy about the data. Okay? Because you should not have gotten a straight line. So just be careful. Okay, make sure your data makes sense. So to me, that looked fishy. All right. Otherwise, the labs were, overall, the labs were fine. Most of the comments I made regarding the lab are typical for this kind of lab, watching your sig figs, no figure captions, things like that. Those were the issues. So go over the email I sent you regarding Ohm's Law. Okay. Questions or concerns? All right. So I want to talk about now the scope, the oscilloscope. Okay. If you're going to become an electrical engineer, this is the most important tool you will learn how to use in your field. Okay. Now, what is the purpose of the oscilloscope? Well, it's to measure signals that vary with time. You can't use a multimeter to really measure signals that vary with time. This tells you what's actually happening. The scope tells you, you can see what the signal, what's happening when you're measuring the voltage across a component. By the way, an oscilloscope can only measure voltage. It doesn't measure current. The oscilloscope measures voltage as a function of time. Okay? If you want to measure current, let's say, through a resistor, you measure the voltage, divide by the resistance, and you got your current. But it gives, the scope gives you the most information. The multimeter just gives you a number, and that's it. Okay. If you watch the video by Electroboom, like I said, I did not put it in the module because it's not captioned, but if you watch the video by Electroboom, if you do a search, and you type these two words, he'll tell you why, I'll spend 15 minutes telling you why it's important. Okay, he's an electrical engineer. Okay. He goes through a lot of good information. But and he tells you the difference between this and the multimeter. The multimeter just spits out a number, and that's it. Okay. The multimeter is good for DC and nothing else. This is for measuring any kind of signal. So it's important to know how to use it. Whether you're going to be an electrical engineer, a physicist, or an engineer in general, because even if you're a mechanical engineer, you're going to have to learn how to measure signals, because you're going to have to know how sensors work. And you might have to learn how to design some sensors. So even a mechanical engineer will have to know how to use an oscilloscope. Okay. But for an electrical engineer, this is really the main tool. Okay. So the scope, I want to talk about the scope, the front panel of the scope. It looks like a generic one. Looks like what you see here in on the screen. What you see on the left, that gray area, that's the display. That's the area that displays the voltage as a function of time across whatever component you're measuring. And then what you see on the right, they're just control knobs. Okay. So what you see there is basically a generic scope. If you go between various oscilloscopes, the locations of the knobs will vary. And depending how much money you want to spend on the scope, you'll have more features. I'll give you an example. The scope that you're going to be using for the lab is a digital oscilloscope, and it costs about $20. Maybe a little bit more than $20. There's also an oscilloscope that costs $1 million. Okay, basically, if you want to be able to measure signals that are faster and faster and faster, you're going to have to spend more money. Okay. So there's a huge variation in terms of the cost of these scopes. Usually an engineer will have a scope that's probably around $1,000 or $2,000, maybe a little bit more. And again, it all depends on what they're designing. Okay, what they're doing during the career. Are they doing stuff that involves fast timing, or are they basically making simple sensors? Okay. So I want to talk about the front panel of the scope. I'll talk about the display and some of the control features. I won't talk about every control feature. This lab, the document, does talk about what all the knobs do. Okay. This scope has, the generic scope has a focusing and an intensity button. Ours does not. That's kind of set. Okay. And again, we're using a $20 scope. Okay. All right, so let me go to the board and let me draw a picture of the front panel. I'm going to make it bigger than what I did this morning, earlier class. because I got into trouble with space. So here's the front panel. And let me draw the display. Okay, so this is the display. And on the display you have XY axis. Like that. And then I'm going to draw in different color vertical and horizontal lines. I'm going to draw in the grid. These grid lines are equally spaced. See, since I'm doing this freehand, I can't make them equally spaced, okay? And the number of boxes that you're going to see, this depends on the design of your scope. Also, the size of the boxes, the size of each one of these boxes, the size of each one of these boxes varies. On a regular scope, you know, one that you would be using in our lab, each one of these boxes is 1 centimeter by 1 centimeter. For the scope that you're using for your lab, it's not. It's something else. I never measured it. Maybe it's 0.5 centimeter by 0.5 centimeter. I don't remember how big I never measured the box size. But typically for a traditional scope, it's 1 centimeter by 1 centimeter. But they're not all the same. Okay. So on the scope then, this displays your voltage as a function of time. And so this is the screen, and on the screen, then what can be displayed is a signal like that. And so this red thing is called a trace. That's the signal you're observing. The one thing, I mean, this has actually some thickness to it when you see it on the scope. Okay, so that's a trace. So really what I'm looking at is some square wave function from some component in some circuit. And so this has a horizontal axis. The horizontal axis is used to measure time. Okay, the vertical axis is used to measure voltage. And so this allows you to get voltage as a function of time. So let's focus on the horizontal axis. So here in this region, you usually have control knobs for the vertical, the horizontal, and then there's another group for triggering, and I'll talk about the triggering later. Okay, let's talk about the main things this thing will do. So let's focus on horizontal. This is called a time base. Now on our scope, it's going to be completely different. We're not going to have knobs. We're going to have a bunch of buttons, and I'll show you that in a little bit. Okay, but this is traditionally what the scope has. And you can vary this. This basically allows you to change how much time each one of these boxes represents. So it's going to be the number of seconds per division. And what I mean by division is one of these boxes. Okay? And it can vary a lot. Again, this number, this width can, I mean, this 1 centimeter box, or whatever that width of that box is, can represent a very small time interval. Okay? Just depends on how much money you spend on your scope. Because I think ours goes down to 10 microseconds per division. And it goes up to several seconds per division. Although when you're looking at a trace that's several seconds per division, that's a really slow signal. Okay, you just see this thing running across the screen. So let's say I set my time base to 1 millisecond per division. And I want to measure the time from here to here. Basically, the time it takes for my signal to repeat itself. We call it the period. In our labs, we're going to be looking at repetitive signals that are produced by a signal generator. And so the time it takes for the signal to repeat itself is called the period. And it's measured in seconds, and we denote it by the letter T. And this is going to be the number, or the number of seconds per cycle. So one of these is called a cycle. Now, conversely, the number of cycles per second, which is 1 over T, is called a frequency. So if I can measure this period, then I can also determine the frequency, because whatever that number is, I take 1 over that. I have the frequency of the signal. The signal generator puts out a signal based on frequency, the number of cycles it puts out per second. Okay. Oh, I'm sorry, I didn't see your comment, Christopher. So you've used one of these before.
It was on like a scan tool that you hook up to your car. Snap-on makes a scan tool that has a oscilloscope built into it.
Oh, okay, that's cool. So you have an idea of how this works then?
Yeah.
Okay, cool. So let's say I want to measure this. So what I do is I count the number of boxes this is. 1, 2, 3, 4 boxes wide. So it's 4 divisions. And then I'm going to multiply it by my time base, which is 1 millisecond per division. So 4 times 1 is 4, so that gives me 4 milliseconds, because the divisions cancels out. Now the question is, how many sig figs should this number be? Well, this timing is precise. So for our purposes, we're going to assume that this number is exact. Where we have to worry about sig figs is in this number. Because the box, when I draw the box, one of these boxes, and I don't know if you can see it. Hold on a second. I don't know if you can see it in this figure. Let me blow that up. But you can see a bunch of divisions in each of those boxes. So generally, each box has 5 tick marks in it. So let me draw that up here. So each box, this is supposed to be a box, okay, it's supposed to be square, has 5 tick marks. 1, 2, 3, 4, 5. Okay, so basically it's broken up into 0.2 division increments. Now, so I can get another decimal place here. So really what I should write down is 4.0. And this should be 4.0. How precise can I make this measurement? Well, here's the thing, and it's hard to draw this on on here. Generally, when you draw the trace, I'm going to draw a trace. The width of that trace is about half the distance between these two little tick marks. So really, you should not be able to go beyond this decimal place. What it's saying is my uncertainty is going to be 0.1. So I can probably measure to 1/10 at the best. So you should have no more than 1 decimal place here. Okay? And the reason being is the width of this is sufficiently large that you really can't go beyond this decimal place. Okay? Now, what if you want more accuracy? What can you do to get more accuracy in this value? I can make this smaller. I can make this smaller. If I make this smaller, then what's going to happen is I'm going to stretch this out. If I have 10 boxes, if I have more than 10 boxes on my scope, not all of them do, what you see on the screen does not have 10 boxes, but our little scope does. If you have more than 10 boxes, then you can change this to a lower setting. So let's say you get 10 or 11 boxes. That's going to give you another significant figure here, and that'll give you another significant figure here. You're going to get more accuracy and more precision if you can stretch this signal out. Okay? So that's one of the things you can do. If you want to get better values, make this as wide as possible. Now, on the scope, let's look at the vertical axis. On the scope, usually on the scope, there are 2 buttons here for the vertical axis. And the reason why is because traditionally oscilloscopes have 2 inputs. You want an oscilloscope really that has 2 inputs. Why? Because what you want to do is measure the voltage across the component and compare it to the power supply voltage. If you look at a lot of the equations you derive in electrical engineering course, your equation for the voltage across the component is some number times the power supply voltage, or it's some function times the power supply voltage. Okay? And so you want to be able to compare what you're measuring across the component to the power supply voltage. So that you usually have 2 signals going in, which means that you have to have two of these, one for each channel, for each signal. Our oscilloscope only has 1 channel. That's why it's only $20. The one I showed you when I did my demo has 2 channels, but it costs $80. But it has other features in it that ours doesn't have. Okay. So let's try to measure this distance. This distance here is called the amplitude. That's the amplitude of the signal, the maximum voltage. And so we're going to do the same thing. This basically gives you volts. These are the volts per division scale. And you can change them. Okay? The grid doesn't change, but what it does is it changes the size of the trace. It makes the trace bigger or smaller, or taller or shorter. So it's either going to be wider or narrower, or taller or shorter, depending on which one you're adjusting. Okay. So how many divisions high is that? 1, 2, 3. 3.0 divisions times let's pick a value, 1 volt per division. Times 1 volt per division. The divisions cancel and I get 3.0 volts. So the amplitude is 3 volts. So in the lab, the video, you just got to choose your own signal. Choose whatever signal you want from the signal generator. The signal generator can produce a square pulse, it can produce a triangle signal, sawtooth, or a sine function. Just pick one of them, and pick a frequency and just some random voltage. By the way, when you pick a frequency, pick a nice number, like 1,000, 500, so that when you take the reciprocal of it, you get a nice number. Don't pick a frequency of 1,359 hertz, but pick a frequency of like 1,000, 800, 400, so when you take the reciprocal of it, you get a nice number. You don't get some bizarre, some long, some value that's just repetitive, like 0.33333. Don't pick like 3,000 hertz, okay, or 300 hertz. Is that clear, everybody? So are we clear about how to make these measurements? I mean, what these things do? There's other knobs on there, right? There's a knob that allows you to adjust the vertical position and the horizontal position, the focusing. Obviously, there's an on-off button. Okay, but let me say something about another important set of controls on the scope, and they have to do with something called triggering. And they're very important. They're hard to learn. This is not going to be the focus of this lab. I basically need you to be able to make this measurement. And as we proceed with the labs this semester, we might say some more things about triggering. But what is triggering? There's several aspects to triggering. Number one, you can tell the scope whether or not you want to measure start measuring the signal either when the signal is rising or going down. You can tell the scope to start measuring at a particular voltage level. Okay, and there's knobs for that. Of course, on an analog scope like the one we have in the lab, you just have knobs and then you can just adjust the voltage level until you see the right one where you want to start at. And then there's a plus or minus button on it so that you can switch it to positive edge or negative edge, meaning rising or falling. So you can tell it to measure whenever you want. Okay? So you can set the conditions on the scope for making the measurements. Where do you want it to start at? Where do you want to look for? Okay. And then the scope can trigger in different ways. So there's a couple of triggering mechanisms. There's one called auto triggering. What it does is this. When a scope is trying to display a signal, it waits to give you a display until the conditions that you set up are met. In auto triggering, if the signal does not meet the criteria you want in a certain period of time, it'll just display whatever it has, whatever it measures. Okay, so it'll always display something. Okay, and auto triggering is good because you want to be able to see something. Okay, you want to be able to see what's coming out of your element, and so auto triggering is good in that sense. But if you want to look at something particular, there's something called normal triggering. There's a button called normal triggering, and so that the scope waits to display anything until conditions are met. Once the conditions are met, then you get a display. Our scope also has a single mode where it'll just take a snapshot of the trace and then hold it for you. So you can take a camera and take a picture of it. So we have a lab. The next lab, you're going to be looking at what's called an RLC circuit. And all I want you to do for it is to set up the circuit and make it work, and then take a snapshot of the trace. Tell me about the circuit, and then tell me about the trace that you get. Okay? And the regular scopes have that too. Some scopes have a memory feature which will actually save the trace. It's kind of what we have in ours is kind of like storing something in memory, but it's for only a short period of time. One more thing I want to say about, let's say measuring the period. Why would you want to measure the period? Why would you want to measure time? Sometimes it's important to understand how fast this signal is rising. If timing is critical, if you're building something or working something that involves timing, this rise time might be important, because if you're measuring something very fast, okay, whatever you're trying to measure, or your signal the signal you're trying to create has to have a very short rise times if you're trying to measure short time intervals. So you can actually measure this rise time on some scopes, not ours. Okay. It's hard to see the rise time from the signal generator on our scope, but if you have a really good one, you can see it. Now, when you do an RC circuit, if you remember the RC circuit, I should have demonstrated it to you. You can actually measure this rise time very easily, because the resistor slows down how fast the capacitor charges up. So you can measure that rise time. But in general, something coming out of the signal generator using our scopes is very difficult to measure the time it takes to go from here to here. But if you have a good scope, you can measure it. Questions? Everything okay? Anything unclear? Okay. So let me show you our scope. So I'm going to have to unplug the microphone. So let me know if it's hard to hear me. My other camera. So what you see there are this is the scope that came with your kit. It's either going to be black or white. Okay, so this is your scope. It doesn't look like what you see in the document. It only has one channel, one input. I don't know if you can see the other one. This is the my scope. The camera. This is my scope. This one has two inputs. This is the one I use for the RC demo. Okay. So it has one input, and it has a knob. So it has an on-off button at the bottom. It has a knob, so you can actually look at just AC signals. You can ground it so that you can adjust where your zero is. Or you can look at both AC and DC at the same time. The fancy term is AC coupling, DC coupling. Okay. Right now I have it set to ground, so what I can do is adjust this vertically. I actually have to press this button twice. Once. Oh, I'm sorry. Let me do it again. You press this button twice, and then I can adjust the location of this trace. So I want to put it along the x-axis, so I did it like that. Okay, so let me take it off ground and put on AC. So this is the input to the scope. This one is. You should have some cables with alligator clips on them. And then this is the signal generator. It's very difficult to see the display because it's bright. And maybe if I adjust the positioning. Can you folks see the display a little bit? Can you see this display? Okay. Okay, it's kind of bright. So this thing costs about 30 bucks. It's not that great, okay? A good one, really a good one will cost about $400 or $500. It has some problems with it, and we're going to experience the problems next week. Okay? When we actually have a lab where we make a measurement. So let me take the output from the signal generator. Again, you have a cable like this with alligator clips. And I'm going to connect the red to the red. You don't want to get these crossed up because usually in the scope, the black is grounded. Not all scopes are like that. Okay, something wrong. I have cranked up. And so there's the signal from the signal generator. I have the signal generator on. I have the signal generator. I don't know if you can see it. It's set to 400 hertz sine wave. Can you see the 400? Because I can barely see it. And I can vary the voltage. Notice that if I put too much voltage on it, the signal gets clipped. And the reason why is because this darn thing can only put out about 25 milliamps before signal gets clipped. So there are a lot of limitations on this thing. That's why I guess it's 30 bucks. Okay. So there will be a lot of limitations there. We're going to actually have to put in really slow voltage signals in order to do our labs. Like 0.3 volts, 0.2 volts, so really small signals. When you start getting to small voltages, the surroundings can interfere. Okay. So that could be a problem. But right now, I'm getting a nice clean signal of several volts. I have this set to 5 volts per division. So let me show you some of the features of this thing. In the document, there's a document on how this works. So this is the name of the brand name is ETEPON. I'm not sure what that stands for, but that's the name brand. Okay. I'm going to press the volts per division button. So you don't have a knob. I mean, you don't have a knob. You just have buttons here. So when I click on it and that box is outlined, I can actually change the vertical scale. Let me make the signal smaller. Let me change it to 1 volt per division. 1 volt per division. Let's see if I can make this. Can you guys see the grid on the scope? Yeah, I guess you can see the grid. And can you see the little tick marks between the grids? That might be hard to see. But when you hold it in your hand, you can see the tick marks in between the major grid lines. So notice I can, as I change, if I go to a lower voltage, it makes the display bigger. If I go to a higher voltage per division, it makes the display smaller. Typically what you want is you want to make the display as big as possible so you get more accuracy. The more boxes you can measure, the more accuracy you'll have. Because if you do something like this for the same signal, you're not going to get a very accurate value for the voltage, right? All I'm doing is changing the volts per division. It's the same signal, but it's much more accurate to measure the signal here. The fancy scopes have all kind of fancy things, like you can actually change the horizontal scale by a factor of 10. There's a button on a lot of the scopes where they call it a times 10. Well, you can actually expand the horizontal scale by a factor of 10. There's also special probes. This one doesn't have the special probe, but my $80 one has a special probe on it, so I can actually change the voltage scale by a factor of 10. So I can actually measure much larger voltages with it. So this one, this blue one, actually has a special times 10 probe. So I can actually measure higher voltages with it. Now, so when I press the button, the voltage per division button the second time, I can actually use it to move the signal up and down. Can you see that? I'm actually moving the signal up and down. Now, the second button is your time scale. Watch what happens when I adjust my time scale. I can go down to 10 microseconds per division, or I can go way up to 5 milliseconds. But then at 5 milliseconds, it's hard to see anything. You want to stretch out one cycle as much as you can. If I click this again, I can actually move horizontally my trace. Basically, I'm telling it where I should start measuring. Is everybody clear on that?
Yes.
Okay. The third button is a triggering button. So right now I have it on auto. Actually, let me change this. Right now I have it on auto. Okay. If I set it to norm, then it will not do a display, and it will not show you a display until it meets certain conditions. Now, the conditions are met very easily, so you can see the signal. There's also a single one where on the single one, it just shows you one trace. It's a frozen snapshot. Okay. And then to go back and get started again, you have to hit the OK button. Oh, I got to change this. Sorry. I'm going to go back to auto and hit OK. And then this last button. Oops, sorry. This last button here, basically you're telling it whether or not you want to look at a rising signal or a falling signal. When you look on the left, when I change this, you notice how it either triggers on a rising or falling signal. Let me go back to this. I'm going to hit it a second time. When I hit it a second time, it's going to allow me to adjust that blue thing on the right-hand side. And that's my triggering level. Okay. Let me change this. By the way, you see where it says AC there? If I change it to DC, so that'll say DC, then this will say ground. Okay. You see the numerical displays on the screen? The numbers? Don't trust them. I'm going to take a snapshot. That one's okay. Let me try it again. I don't know if you can see the frequency there is varying, even though it's set to 400 hertz. So that number is hard to trust. What I would do if I were you, I would just make the measurements directly, the way I showed you how to make the measurements. Don't trust these numbers up here, okay? Because those come from some sort of averaging method. And so at any instant, that number might not be accurate. One more interesting feature this has is this. Let me disconnect. There's a little tab up here. And the little tab is a signal generator. It's just a signal generator. So I'm just going to connect the positive end here. It puts out a one. I gotta connect it better. It puts out a 1,000 hertz signal, so you can use it to calibrate your scope. Okay, so this little tab is actually putting out a signal. It's a standardized signal, so you can use, all scopes have that. All scopes are usually calibrated to a 1,000 hertz signal. Okay, But don't use this for your oscilloscope quiz. Use this. Okay, because you need to learn how to use that. So let me show you the signal generator real quick. Let me connect signal generator to the scope. Basically, it's got to do this. The red to the red. Black to the black. So there's a button that says start stop. You can only change things when you get out of when it's not running. So I'm going to turn it off. And then on mode, if I press the mode button, I can change the signal. Can you see that it says square now? So when I turn it on, you see a square pulse in the trace. Let me turn it off and hit mode again. Now it's going to give me a triangle pulse. Let me turn that off and then hit mode again. That's a sawtooth. Anyway, there's a whole bunch of them. And some of them are really not going to have any use to us. But I guess the person who designed this got creative with it. There's an EKG one, and there's one actually for white noise. Let me go back to sine. Okay, so there's our sine function. Now we can change the frequency, and this is more of a pain. So I'm back, I'm in the off mode. When you see the cursor there, then you can change the frequency. If I click the plus button, I can go up in frequency, or I can go, if I hit the minus button, I can go down in frequency. If I want to go to the next decimal place, then I hit the cursor button, and I get to the next decimal place, and then I can press the plus and minus button. So the cursor button allows me to change the decimal place. Make sure that this button is sticking up. This is a DC offset. You want that to be, and nobody knows what this is for, so don't worry about it. Okay. Even when I look online, nobody knows what it's for. The manual doesn't have a good description of it. It doesn't really say anything useful about it. Any questions about the scope or the signal generator? Yeah, the signal generator is actually not that hard to use. You just got to learn how to use a scope. You're just playing with a bunch of buttons. And this one's pretty simple compared to a regular scope because there's not a lot of features on it. So in part one of your lab, what you're going to do is you're going to pick a signal. I don't care what signal you want. You want sine, square, triangle, sawtooth, and then measure the period, the frequency, and the amplitude of the signal. Just show me in the video you know how to do that. So I'm hoping the video is no more than a minute. If it goes over the minute, I hope more than a minute, maybe it's no more than 2 minutes. Okay, should be short. Almost everybody gets full credit for this part of the lab. I mean, last semester only one person who did it completely wrong. But otherwise everybody got full credit for that part of the lab. The second part of the lab, we have to characterize the signal generator. We actually got to measure its resistance. And the term, the correct term is not resistance, it's impedance. Because impedance includes capacitive effects and inductive effects. So we got to measure the impedance of that power supply, the signal generator. And we're not going to use a scope to do it because if we did it with the scope, it would actually take a long time to do it. We're going to have to use the multimeter. So, let me go through the document. We go to part 2 of the lab. We'll characterize the signal generator. So what you're going to do is you're going to collect the data for this table. And the software will generate everything for you. I mean, the Excel file will generate the calculated impedances. So what you're going to do is this. You're going to take a 100 ohm resistor and you're going to measure its resistance. Okay? Then, let's go back to the other display. Then what you're going to do is the following. You're going to take a multimeter, the big one. So take the big multimeter, okay, and you're going to measure the voltage coming out of this thing. So you have a yellow and a red cable that came with your kit, so you want to connect it to your big multimeter. And you want to measure AC voltage, because this is a sine function, you're not measuring DC voltage. You're going to be measuring AC voltage. You're going to actually have it set to the 2-volt scale, because you want to put out you want this thing to put out about 0.3 volts. The reason why it's got to be that low is because otherwise you're going to draw too much current and it's going to mess everything up. Okay, so you want to set that up to 0.3 volts, but that 0.3 volts that this thing is measuring is really a root mean square average voltage. It's not the amplitude. You're actually measuring of average. And we'll talk about the root mean square voltage when we get to chapter 33 of the textbook. That's in the next unit. Okay, so let me make the connections. I'm going to measure the voltage across the signal generator. And I gotta turn it on. So right now it's measuring the voltage across the signal generator. That's an RMS voltage. It's not a peak voltage. Okay, so I'm just measuring. Notice the scale I have it on. It's the orange side. You got to be measuring AC voltage. So you measure the voltage across the power supply. Then you connect your signal generator to a 100 ohm resistor. You don't have to use a printed circuit board for this. You can do it however you want. You connect it to a 100 ohm resistor. Make sure you measure its resistance. And then take the multimeter and measure the voltage across this. And you'll get a different voltage. And the reason why is because there's a resistance in here. This has an effective resistance. Let me go on the board and draw a picture of what's going on. Okay, so let's pretend signal generator. Okay? So this is ideal. But a real one acts as if there's a resistance across it. We'll call it our generator. So what you're going to do is you're going to measure the voltage across the signal generator. We'll get a value. This is called the open circuit voltage. Okay. Now you connect a 100 ohm resistor. So basically what you have is a voltage divider circuit. So what you're measuring, theoretically what you're measuring is this. Okay? You're not getting the full voltage from the power supply because some of it is across this thing. And so You can solve for our generator. You're going to measure this. You're going to measure this. Oops. And Excel will calculate this for you. If you rearrange it like this. And this will vary with frequency. So you're going to fill out the data table. You're going to do this at a bunch of different frequencies, and you'll see how this number varies. The value's higher at lower frequencies, and then it kind of stabilizes. And all I need you to do is fill out that data table because you're going to use that information in the next lab. Questions? We okay? You guys still there? You guys are quiet today. Okay, still working on the last lab. Okay, that's fine. Yeah, this lab shouldn't be that hard. You'll be fine. I mean, this lab should be okay. You can get it done kind of quick. Okay, that's fine. That's fine. All right, so I'm going to end it here. I'll see you guys at 2 o'clock.
Thank you.
Okay.